So as I was saying, this is the second presentation today about disaggregation and advanced packaging. But I'm not going to touch the topic of how we test die-to-die connectivity. We're going to take this to a different direction and talk about a little bit about the challenges and a lot about the opportunities for test time when we're doing disaggregated products. So we're going to cover why disaggregated, why we're seeing more and more advanced packaging in disaggregated products. We're going to talk just a little bit about the test challenges and, as I said, the opportunities. And then we're going to dive into Intel's latest product where we applied a different strategy than usual for disaggregated client product and introduced what we did with fast I/O and HTTP high performance test port and the conclusion and then Q&A if we'll have time for that. So let's start with the why disaggregation. So in the recent years, we've seen development in interconnect technology, both from Intel and mainly from Intel and TSMC, a 3D SoIC or CoWoS or in Intel Foveros or EMIB are all different technologies for doing on-chip connectivity and not on-package connectivity. And this was a major drive into disaggregated products or making new products where we can simply or more simple than in the past, more simply than in the past, divide the chip into multiple chips and decide on where the barrier actually exists. And this gives us a couple of advantages. The first one is, as it says here, playing to the process's strength. It was mentioned in previous presentation today, where each process has its different characteristics, and this allows us to pick the right process for the right functionality. We see older and more reliable processes picked for I/O devices, where the analog devices stability is very important. We see more advanced processes like the N3, N2, or Intel's 20A, 18A picked for where we need performance. And we see maybe a compromise between newest and best and stable processes for other functionality, just like graphics or AI. The second advantage that the disaggregation allows us is to fit the die to reticle, meaning that we can fit the reticle, and this was mentioned here as well before, but it also provides us the opportunity of getting really high LFUs, the utilization of the lithographic field. I believe most products today are aiming at 90% plus in order to cut costs, and anything below that is going to really reflect in the product cost. Disaggregation and deciding where the disaggregation line is and how we can use different floor plans for our products allows us to improve overall our LFU. The third topic is the yield. Lower die sizes means better yield, but even beyond the die sizes itself, it provides us the capability to do pre-assembly sort testing, pre-assembly wafer testing, and therefore assemble only good parts, eventually reaching higher yield on the overall product. And the last thing that it allows us, it improves time to market for different SKUs, for allowing us to provide a new product just by changing one piece. And we see this today where we have products in which only one chip changes, perhaps newer cores, newer generation of cores, but all the peripherals stay the same. And for those products, the time to market is insanely quick relative to what it used to be in the past. So all of those are drivers for this change, and we're seeing more and more products using this disaggregation and 2.5D or 3D construction. But it brings about challenges as well as opportunities. So for challenges, we have, first of all, we have multiple test platforms now. We have, before we used to do sort wafer testing and then package testing, but it more or less looked the same. Now we have sort wafer testing for individual dies, and then once we assemble them, we would want to test the assembly before packaging. And then after packaging, we're doing the final testing where we have class testing, binning, PPV, CMV, etc. So that means more testing platforms, it means multiple retargeting targets. We need to have our content ready to run at different targets, sometimes at the die level, sometimes at the package level, and these are different, and we need to validate all of them. That's the first challenge. The second challenge is that due to these different platforms, we need to be able to access the tests. We need to, provide test access to all the dies in all configurations. This means that both the JTAG needs to be available, and if we're using a parallel test port, this also needs to be available at all levels, both at sort wafer testing and at class package level testing. The second challenge is inter-die connectivity testing. This was discussed in a presentation before, so I'm not going to dive into that, but that's a different type of test that we will need to develop. We would need to still define, despite the fact that we are now assembling die on die and die to die, we need to remain compliant with current standards because this is what our equipment expects. IEEE standards 1149, 1687, 1838, if one chooses to implement that, we need to remain compatible to that. But on top of all these challenges, we also have one major opportunity, and that's what I'm going to focus on in this presentation. And this opportunity is the concurrency of our testing, meaning that if we were able to actually, on packaged part, test each die concurrently at the same time, separately from the other dies, we could benefit a lot on the test time. It would mean that basically we would have one die that probably would be dominant in its test time, and all the other dies' test time is going to hide behind that, and we're not going to feel them. And once we improve that one die, we're going to improve our overall test time. And the disaggregation in general favors this kind of implementation because the architecture, because we're already talking about different dies and assembly of them, the architecture is probably going to be prone to simple isolation in terms of power delivery, test infrastructure, etc. And I'm going to dive into that over the next slides. So before the actual implementation, some intro on Intel next-gen client CPU. So the next-gen client CPU is composed of a 2.5D construction. It is using Foveros technology. It's composed of 3 dies, the CPU die, which is the biggest and by far the most dominant in terms of test time. It's also manufactured on the Intel's Intel's newest process, the 18A. We have an SoC die, which holds most peripheral functions of the CPU, and we have a separated graphics die, which has a graphics accelerator on that. In terms of functional IOs, and it's important to remember this picture because we're going to come back to that when we're talking about what IOs are available for us to use. Most of the IOs in this package are in the SoC die, which handles peripherals. We have a very limited number of IOs in the CPU die, but those are high-speed DDR IOs, which for a number of reasons we cannot use them for test, neither at sort or at package part. So we're going to need different IOs. Okay, just remember that. As far as system JTAG access, so we have a single JTAG access port at the SoC die, and then that JTAG network traverses through the CPU die and over the die-to-die Foveros connection, and from the CPU die to the graphics die. All of this is done through a proprietary architecture. It's not 1149. It's not 1867. It's based on 1149. It's compatible with 1149, but it's Intel inside architecture. But basically, we have the important thing to note is that we have a single point of JTAG access, of JTAG test port. Now, because we need to test each die separately at the wafer sort level, each die also has probe bumps. Those probe bumps are available both for JTAG and for the parallel test port. And obviously, we mux them in each die in order to be able to access each die separately at the sort level, when doing wafer sort. Each die has its own JTAG network. This JTAG network is composed of 1149 slave taps and 1687 instruments. It's a mixed, it's a hybrid network. But more importantly to note is that other in the HVM use case, in the sort wafer use case, each one of these dies is able to operate its JTAG network independently. And that's critical for the next step. Each die also implements Tessent memory BIST. It has a self-sustained eFuses, BIRA, BIZER solution. There's no resource sharing between the dies. Each die is a standalone die in that term. And additionally, each die has a full Tessent SSN fabric. Each die also has some different bandwidths. The CPU die, as we mentioned earlier, it's by far the most dominant in terms of test time, has a 64-bit SSN network running at 400 megahertz. The SoC die has a 32-bit network, and the graphics die has a 12-bit network. All of them are running at 400 megahertz. Now, with that in mind, our goal for this product was to allow full concurrency of die testing on a packaged part, meaning that even once we package them, take it into class, we're going to be able to access the CPU, SoC, graphics die, and this concurrency includes complete independence, meaning no pass-throughs, no test signals, no power issue, no power signals, nothing is a pass-through through other dies, so we can completely reset one die while we're doing testing to the other die. This was critical in order to have zero dependency between the test programs. There are actually 3 test programs running here, or this was our goal. The second goal, once we do that, we allow full pattern reuse between wafer sort and the package class testing. We might need a variant of HVM reset or a neat, but the actual pattern is going to run exactly the same. That was one of the goals: reuse of patterns, one-time validation. Same pattern runs on all our platforms. The requirement for that, as we already said, was a full inter-die isolation. This referred to 1, power pins, power isolation. Each of these dies is derived from a different power on HVM. Even if on system it's shorted to the same voltage regulator, on HVM we drove them through different power planes. Reset signals, basic signals which control reset and in functional mode are traversed over die to die. We had to alter them and route them through the board, meaning they were pinned out from the package and back into the package, so we can control them in the HVM. And isolation of the Foveris link isolation, so we can completely isolate the link between the dies. The other element that it required is to pin out the JTAG and the parallel test port, the one that we're using for sort testing. We needed to pin that out as package level pins. Now, because these are very large networks, this sums up to around 160 pins that we needed to expose to the package. This was a catastrophe. This means that, one, we had to either enlarge the package, which has a huge product cost impact, and basically means that the test time saving that we're doing means nothing because the silicon area costs more, or that, and sorry, not or, but in addition to being non-package compatible to previous products, which was also unacceptable. So we had to find another solution, and that solution is what we're going to talk about next. So our solution for this was using a new technology coming from Tessent called Fast I/O, as well, in addition to our implementation of a high-performance test board, HPTP. Now, the HPTP itself is a custom I/O. We designed it ourselves, but it doesn't have to be this way. It can be any fast I/O that you are familiar with. It can be PCIe or UCIe or anything other than that. We used a custom I/O and a protocol-less data because it provided us better bandwidth. We didn't need any further translation into another protocol, and we could use native Tessent retargeting patterns, but we're going to talk about that in the next slide. In order to simplify our design for the HPTP, We used single-ended I/O. We used a double data rate protocol with clock speeds of up to 800 megahertz. We didn't want to stretch ourselves too much because of the higher costs for testers. We need to drive higher than that. So 800 megahertz providing us with 1.6 gigabits per second per lane. Overall, for the CPU die, we had 16 lanes, 16 in, 16 out, which provide us with an overall of a 25.6 gigabit per second for the test board. Now, how does this work? So the tester sees 16 pins, and this goes through the Tessent Fast I/O. The Tessent Fast I/O allows us to expand our test bus from a very narrow high-speed I/O to a wider slow-speed SSN. We use pretty standard components, the bus frequency divider and the bus frequency multiplier coming from Tessent. These are not new, but their usage is new. And specifically in this case, we wanted 16 pins, 16 lanes, but we could not fit 16 lanes all in one place because of package issues and floor plan issues. We could not place them all in the same time, so we split them. We had a split HPTP port, meaning eight lanes in one place, 8 lanes in another place. Tessent retargeting had no issue with handling that. There are different number of repeaters where you see the repeater, the pipe stages. We had different number of pipe stages going from the HPTP into the BFD components and onto the SSN network. That works fine as well. That gave us freedom to place the I/O where we need it, pipe stage as much as we need it on its route to the BFD components and to the DiskU FIFOs, eventually creating a single SSN fabric with a 64-bit width. The integration of these components, as you could imagine, since these are standard components generated by Tessent, is seamless. The retargeting that we did for these patterns, again, it's all part of the Tessent Fast I/O, so it's seamless. Tessent doesn't really care if you retarget to a full wide I/O going at 400 megahertz or to a very narrow channel doing double data rate at a higher frequency. It handles it seamlessly. You can even create 2 retargeting targets, one to a very wide network, which is slow speed, one to a very narrow fabric, which is high speed. It all just works out of the box. In terms of the I/O itself, since we were running at 1.6 gigabit max frequency, we had a calibration routine. We didn't have to have multiple calibration routines per temperature, per frequency, etc. One-time calibration routine for these kind of frequencies is enough. Possibly, if we ever go to higher frequencies, we're going to have multiple calibration points and multiple configurations in order to make it work. So, all in all, we tested the HPTP and the Tessent components on a test chip before the actual product. We developed the calibration routines on this test chip to be ready for the actual product. The overall increase in pin count was 46 pins in all. If you remember, the original number was 160, so we managed to squeeze this goodness to 46 pins. Most of them were allocated into NCTF regions, meaning that there was zero impact on the package itself. And from package design perspective, it's a don't care. We didn't have any post-silicon bugs, any retargeting bugs that we've observed using the fast I/O technology. We did full validation, both pre-silicon validation in a Siemens test bench or Tessent test bench, and on the full design using style patterns. Before, we didn't observe any special bugs or issues pre-silicon, neither did we observe them post-silicon. In terms of reduction of test time, we managed to reduce around, depending on the actual SKU, we managed to reduce between 10 to 25% of the test time using this method, which accounts for around 50 million across the current volume And this is expected to grow as the volume grows. As what? No one counts money, except when it comes to the licenses. Uh, it was a cheap shot, I know. In terms of the future of Tessent Fast I/O, Tessent Fast I/O is now POR for all the client products. We're going to use it on the next gens as well, and then we were exploring how to even better utilize this technology, meaning reaching up to higher frequencies and using asymmetric HPTP. As you've seen, the current implementation is symmetric. It doesn't really have any importance because our current SoC design doesn't really have multiplied multi-instantiated blocks. So the on-chip compare doesn't really come into play. Once we have those multi-instantiated blocks, and OCC is going to make a big difference. Asymmetric HPTP with having the choice of turning output channels into input channels, increasing input bandwidth is going to matter, and we're going to look at that for the future. And the third, and maybe most important future developments is new contact technologies, meaning topside, things like topside contacts, sync-less contacts, and ways where we can actually increase our pin count and take advantage of this technology and take advantage of concurrent testing without impacting the package or the number of package pins that we need. That's it. Questions?